Thank you, Edo. That was really fantastic. It's really a pleasure to be here and getting to know many great colleagues and learning about the work they do. I wanted to start the presentation maybe by thanking Tian, who gave a great introduction to the topic of trustworthy AI. And maybe I wanted to have a question for all of you. How many of you trust AI? How many of you can provide explanations for why AI algorithms make the predictions they make? So it's very clear that deep networks are all over the place, and they're having really a great impact in many, many applications. It all started in 2012 with great results in computer vision with ImageNet. But today, you have AI driving recognition of speech in Siri. They are powering self-driving cars. They're powering the recognition of products in Amazon Go. And so, they're everywhere. And as these algorithms get deployed, well, they are going to impact us as humans. And therefore, it's important to make sure that these algorithms are trustworthy. What does that trustworthy mean? It means probably that you want these algorithms to make predictions that are accurate, and so you want to put error bars on the predictions of these algorithms. It means that you want these algorithms to be safe, right? You don't want the car to crash because of an error in the detection, say, of a pedestrian as the car was driving. You want these algorithms to maybe be fair. Perhaps you're trying to predict whether to give credit to someone or not, and you are going to have a set of protected groups, say female versus male, and you would like the, if you give credit, you want the algorithm to make sort of the same predictions over these protected groups, or similar to some extent. But another question, perhaps, that involves trustworthiness is this question of explainability. In many cases, maybe you don't care, right? When you accelerate in the car, why do you care about why it did accelerate when you press the gas pedal? Probably not at this point, right? It's become trustworthy eventually, what's happening there. But in many cases, right, that you don't quite understand why the algorithm made a prediction, you may actually care about having an explanation of what was the reasoning that led the algorithm to make that prediction. So when we think about the many algorithms from statistics and computer science and machine learning, there seems to be a belief that there is a little bit of a trade-off. That if you want your algorithms to be really accurate, today, right, we have to use deep networks. They're black boxes. We don't understand what features they're learning and why they make the predictions they made. We don't understand when they fail, why they failed. At the other end, we can have, on the far right, algorithms that are highly interpretable. They're based on prediction rules. They're maybe based on physical models of a phenomenon. And so we understand what every variable means, and so we can understand them. And there are some models like linear regression decision trees that we all believe to be interpretable, like regression with sparsity, which variables are the most important that we selected. But are they really interpretable, or is it that they're just interpretables because the variables had a meaning? And what is the right trade-off? Because if they're going to be highly interpretable but not very accurate, then maybe some of us will be okay with, it's just accurate even if I don't know why it works. So here's one example of one type of algorithm that is considered typically to be highly interpretable, and it's a decision tree. And I am not an expert on decision trees, but by and large, my understanding is that data comes in and you make a decision. And if it is, say, less than 0.5, you go to the left. If it is bigger than 0.5, you go to the right. And then once you are in this node, you again make a decision, and eventually you arrive at the leaves. And when you arrive at the leaves, typically you predict. So let's say it was a classification task, and you just go asking these questions, and you decide. And so the issue is that if those decisions are based on variables that we as humans decide, or that the modeler decides, maybe the accuracy is not very good. And so people said, well, what about just learning the decisions that are made in each one of the nodes? And there is now these deep neural decision trees where you have neural networks that actually make each one of those decisions. And so what we did was to take, in this case, a deep neural decision tree that had been trained for the task of predicting the class of birds in an image. Okay? And I have no idea how humans predict birds. I'm told that you look at attributes. But therefore, what we wanted to do here was simply, let's look at this root node. Now, this was learned, so it's a variable that is unexplainable. You don't know what it means. And now let's look what it means to be bigger than 0.5 versus less than 0.5. And maybe you can see from that distance. But the question I'm asking you is, do you see any pattern that emerges, like that distinguishes the images on the left versus those in the right? I've looked at them, and I, as a human, can't tell a particular pattern. So this is, to me, one example that if you actually learn the decision rules, they might not be explainable. It might not be a particular reason, or maybe there is, right? But it might be something hard to parse as to what is it that the D1 feature is looking at in order to decide whether to go left or right. So because of this, because the algorithms that are expected to be interpretable don't perform so well, what the current trend really is, let's just take the deep networks. They are highly accurate. We're going to use them. And then let's try to explain a posteriori what the neural network is doing. And the way by which these explanations, at least in computer vision, people have looked at them is, well, if I'm trying to predict, say, from an MRI scan, whether a patient has Alzheimer's or not, the way in which this is done today is you simply ask, well, you look at the prediction that was made, Alzheimer's, and you try to look what regions in the image are the ones that contributed the most to that prediction. There are lots of methods to do that. They produce these heat maps. So what you see in that heat map there is that the red regions are the ones that were deemed to be the most informative for prediction. How is this most informative done? Typically, you have algorithms, and GradCam, the grad stands for gradient. And what they typically do, okay, they do a lot more sophisticated things that I'm grossly oversimplifying, but by and large, they compute the derivative of what you're trying to predict with respect to the feature of a particular pixel, and they look for regions that have very large derivative. Okay? Because it's therefore the prediction is more sensitive to changes on that input, and that's why they're looked at. But what happens is that you look at the results, and now people are just debating as to why that region was informative or important for making that decision. And so rather than coming up with a definition of what interpretable should mean first, and then develop an algorithm that you assess based on that definition of explainable, people are just coming up with algorithms, and then the algorithm produces explanations. So the definition of the explanation is the algorithm itself, to some extent. So the good is that you can apply these to every deep network that was designed, and you don't need to retrain it, right? You just compute these derivatives of the outputs with respect to inputs, and you produce these heat maps. But the bad is, as I said, it's very hard to understand why these predictions make sense. Why are they really providing explanations as to what the model does? Salient parts of the images may be the informative or may be good explanations, but they may not. Okay? And so this has led people in the field, and this is a colleague from Carnegie Mellon, to really be very, very critical of the state of the art with explainable AI. That, he says, most of it is really nonsense. The quote at the bottom says, the precarious state of interpretable deep learning is that we should be far more scared upon hearing that a hospital or government deploys any such technique than upon hearing that they haven't. So what do we do? What we are advocating is that we shouldn't be thinking about explainability post hoc, a posteriori, but rather we should think about it from the beginning. Ideally, we should have a definition of what it means to be explainable. I'm not going to be so pretentious to say that I have that definition, and probably it'll take our field 10 years to come up with a good definition of explainability. But I'm going to propose one that hopefully it makes sense to some extent, and we're going to be working with that. But explainable by design then means you come up with a definition of what it means to be explainable, and then you try to design algorithms that produce those explanations. The second one is that we conjecture or postulate that explainability needs to be to the user. It needs to be in terms of words that are meaningful to the user for that task. Okay, it could be in terms of some symbols. It maybe doesn't need to be word or some patterns. But these explanations are domain dependent, task dependent, user dependent. What do I mean by that? Well, if I'm speaking about AI to a crowd like these, we're all statisticians, right? I can use certain words and certain terminology and certain way of explaining, and you will understand what I'm talking about. But say if I'm explaining that to my father who didn't go to college, I'm going to adjust the vocabulary and explain the same thing in very different terms. So the user matters and the words that I use. The same is true, right, if you've got a clinician explaining why he made some diagnosis to another clinician, he's going to use certain vocabulary. He knows that the other person is highly trained and they will be able to communicate. But if the clinician is explaining that to the patient, he's going to use a different vocabulary and a different way of explaining, right? So the user matters. The task matters, right, because the words that I use are going to change from one task, say clinical decision making, to giving a lecture in AI. And the domain as well is going to impact. So how could we come up with any definition of explainability that captures these notions that needs to be user-dependent and task-dependent? So what we are going to argue, and this doesn't need to be the way to go, but one way to do it is that we let the user come up with what we call a query set. What is a query set? It's going to be a very large, let's say 1 million set of questions, right? And questions about, questions that matter. And the main point is that if I, or if the AI system is able to answer all of these questions to the user, then the user will be satisfied that this was explainable. Okay? I'll provide examples in the next slide. And then what an explanation is going to be, our definition of explanation, is that it's going to be a sequence of questions and answers, right? And hopefully, I don't need 1 million. Hopefully, with 3, 4, or 5 is sufficient. And naturally, we're going to prefer shorter explanations over long explanations. So what are some examples of these query sets? So I'll begin with what I already mentioned. Suppose you want to classify birds. So you go talk to the experts on how birds get classified. And they'll tell you that typically they look at 300 different attributes of the bird. Like, I don't know, is the beak elongated or is the belly yellow? Things like that. So those will be questions, and you can answer them yes or no. If you do computer vision, you might be interested in scene interpretations, and the questions might be whether some object is present or not, whether that person is carrying a bag or not, things like that. Questions about the presence and absence of objects and relationships, geometric relationships between those objects. If you're actually predicting a disease, the set of questions and answers might be the set of symptoms. Do you have this symptom, yes or no? And then you go with one after the other, and after so many, well, you could begin having some of the tests, right? And the response to the tests, right? So this is illustrated here with this example, and green means that the answer was yes, and red means that the answer was no for this particular prediction. Here's another example with text data. You could be trying to predict what is the topic of the document, and maybe you could do that based on asking questions about the document. Or what we did in this case was simply ask far simple. We were just asking what words are present or not. Okay? So hopefully this gives you a sense that this could be applied in many different domains, and that in each case you can relatively easily come up with a vocabulary of questions and answers that are meaningful for solving that task. So, and again, just to provide one concrete example, once we have this query set, what is it that we're going to do? And this is the example with bird classification. So what we're going to do is the image is going to come as an input, and we need to come up with an algorithm that will select what question to ask. What is the first question I should ask? What is the second question that I should ask? And eventually should also decide to stop because it's already satisfied, or because you, with those 7 questions in this case, has shape perching like yes. has belly color yellow? Yes. After 7 questions, you were able to predict, or the AI algorithm is able to predict that this is a green jay with 99% probability. And then you decide to stop because you're happy with 99%. All right? So how do we do that? So the first challenge, naturally, is how do I come up with these questions? So I'm saying the user needs to give me all of these questions. Is that the case? Well, I'd argue, actually, and this is true for some of these image analysis tasks that is like, why did you decide that a 5 is a 5? We may not be able, as humans, to come up with questions about edges and orientations and some of these very localized details. So if we humans aren't able to come up with what these questions are, probably there is nothing to be explained, right? Because if the explanation is going to impact us and we are not able to tell how we want those explanations, that's probably a problem. But naturally, right, you want to automate this. So long term, we would envision the ability to actually learn what these query sets are as well for a given task. But for today, I'm going to assume that the query set is given, and I've already given you 4 examples of the query sets that we're going to be using. The second aspect is that the query set might be very large, millions of questions, and we are going to be selecting the smallest possible number of questions that are sufficient for making that prediction. So Occam's razor's principle. And the third, and this is primarily computations are going to be intractable, we're going to have a greedy procedure for doing that, which is we're going to play 20 questions. We're going to select 1 question at a time in order of information gain. Okay? And I'll explain how we do that in a moment. So the approach is going to be, to some extent, information theoretic, and trying to build on top of information theory but to make it more semantic. So we're going to be having this definition of what semantic bits are as opposed to just bits. We're going to have a definition of a semantic code as opposed to a standard, say, Huffman code. And these concepts of semantic entropy, that is going to be sort of the expected number of questions you need to ask in order to solve a task. All right. Okay, so this is the outline for the rest of the talk. I'll first define all of these concepts, semantic bits, semantic coding, semantic entropy. Then I will describe how we compute. By and large, it's going to be intractable, and we're going to need a lot of deep generative models and a lot of statistical methods to learn them. And then I'll give you a bunch of examples, the same 4 examples that I already mentioned. Okay, so let me begin. So as a matter of notation, Q is going to be the set of questions or the set of queries that I've been talking about thus far. X is going to be a random variable that denotes the input data. So it could be a sample from one of the images of the set of birds. Q of X is going to denote the answer to the question. By and large, this doesn't need to be the case, but for the sake of the talk, think about just binary questions, yes or no. And so this Q of X is therefore a vector of dimension 1,000,000, if you have 1,000,000 questions, that has all of the answers to all of the questions for that X. Okay? So that's the first part. The second one is an assumption of sufficiency of the query set, sufficiency for the task. What do I mean by that? I simply mean that if, and I already said this earlier, if I can answer each and every question, you, the user, will be satisfied that, that I provided an explanation to all of your possible questions. Okay? So that's what I mean sufficient for the task. So in the case of the birds, right, they said that it needed to be 300 and something attributes, and with those, they can classify every bird. But if it had only been 5 attributes, they probably may not be able to classify them. So that's what I mean by sufficient. Of course, you can think of sufficiency, and it is going to be connected to being a sufficient statistics for the task, but I'll mention that in a moment. So what is the task? The task is to predict some variable y, given x, and so in this particular case, you might think of it as just computing the posterior. And what we mean mathematically by sufficient is that the posterior of y given x is the same as the posterior of y given the set of all answers, or given the answers for x. Yeah, the set of all answers for x, and therefore the event here is the set of all inputs that agree with the answers to x, the set of all inputs such that the answers on x prime is the same as q of x. Okay. That's the mathematical definition of being sufficient. And so this immediately leads to the definition of a semantic bit. Each query is going to be considered as a basic semantic unit of information, or a semantic bit. And the sequence of queries and answers is going to define a code. It doesn't need to be an optimal code at this point, if you're familiar with information theory, right? It's convert any input data into a sequence of zeros or ones, and that's an encoder. The encoder is going to be the algorithm that maps the input data to the set of queries that need to be asked and the answers, and it doesn't need to be optimal at this point. But that's exactly the notation here. Code sub q of an e of x is q is the set of queries, e is the encoding algorithm, and the sequence of queries and answers. That's what it is. Okay, so in pictures, by and large, what we're going to be doing is to take an input. We're going to have an encoding algorithm that is going to select out of the million queries, in this case, just 5. And then we're going to answer only of those 5 queries. And then, based only on those 5 questions and answers, we are going to have a decoder, which in this case is expected to predict y, given the code. Okay? That's the intuition. So how do we formulate the question of selecting an algorithm that does this? And so that is where the question of minimality. We want shorter explanations, and shorter explanations are to be preferred to longer explanations. So we use the classical definitions for that purpose, and so here it is. This is the code. The bar means cardinality, so that's the number of questions that I get to ask. Then I'm going to take the expected value with respect to all input data. Okay, so this is really, in classical information theory, the expected code length, and now is the expected semantic code length either way. And what I'm going to do is to select an encoder that minimizes the expected code length. So in other words, you are trying to design this algorithm that's going to select the queries in a way that you produce, on average, for your task, you produce the smallest number of questions. Okay. Subject to the constraint of actually solving the task. And what is the solving the task? Well, the prediction of y given x should be the same as the prediction of y given the code of x. And the code is, in a certain sense, sort of a summary of the entire data set, right? Of the input x. So that's the basic formulation. And it's nice to write definitions. So this is the definition, if you wish, of how you should design the algorithm that is going to produce minimal explanations in the sense of being shorter, and sufficient in the sense of being able to give you the posterior y given x. But now we need to compute. And so how do we possibly compute? And naturally, this is, by and large, intractable. That being said, there are some good properties if you care about, well, does this have any connection with classical Shannon information theory from the 1950s? So the answer is yes. There are some simple cases where this is the case. So Shannon information theory was about reconstruction. You want to take data, compress it, transmit it, and then reconstruct the original data again. So in that case, what you're trying to predict y is the same as x. So, and now q is the set of all possible binary questions about that data. So if that's the case, semantic entropy reduces to the classical notion of Shannon entropy that we learned. The second one is that if y is not equal to x, but is some function of x, and q, again, is the set of all binary queries, then the entropy of y is a lower bound for the semantic entropy between x and y. This is upper bounded by the expected code length, and is upper bounded again by entropy plus 1. This is a little bit akin to the classical theorem about coding theory, that the optimal encoder is within 1 bit from entropy, okay? Or that the expected code length is within 1 bit of entropy. And these are a bunch of other simple properties, like the semantic entropy is non-negative, is 0 only if x is independent from y. And the last property probably is going to be useful moving forward. We haven't explored it yet, but we think it's going to be useful for multitask learning. If you've got many tasks and you're trying to assess, say, complexity, and you think that complexity is this semantic entropy, this is sort of the sub-additivity property, that if you learn or you compute the semantic entropy for 2 tasks together, is less than or equal to the sum of the semantic entropies. But we haven't explored this yet, and it's just to give you a little bit of a flavor that there is some theory behind this definition. So with that in mind, let me go to the next part, which is how do we compute? So computing semantic entropy is generally intractable for many reasons. One reason might be that the number of queries is really large. Well, the optimization problem to find the optimal encoder seems to be incredibly challenging. But in practice, we hope to do better. We hope to do better because the number of queries should be small, right? The most informative ones. How many of you have played 20 questions? Right? So it's called 20 questions because you don't ask, in average, you're expected to ask 20. And how do you choose the questions to be asked? So the other day I was talking to my son, he's 10. And I said, hey, I have a number in my head between 1 and 10. Ask me a question. And he said, is it less than 5? And I told him, why did you ask me if it is less than 5? Oh, well, because then it's kind of it's half and half. He didn't say it splits the space in 2 halves. But by and large, right, the most informative question is going to be the one that splits the space in half, and therefore you can throw away half of the possibilities, right? And that's exactly what this classical algorithm called information pursuit that was originally proposed by my colleague Don Gieman at Hopkins in the 90s. And that's exactly what it does. So I'll go through it because it's incredibly simple. So here it is. X is a random variable, Y is a random variable, and I here is classical mutual information. So what you're trying to do is select the first query is going to be selected as the query that maximizes the mutual information between the answer and what you're trying to predict, which is Y. And that's how you select the first query. Note that the first query is a function of the distribution of the input and output data. I've not seen any particular image yet to decide what attributes should I ask, okay? So this first one is the most informative attribute overall without having seen the image yet. And so in the case of the example for my son, he just said, is it less than 5? Like he didn't know anything about what number I had in mind. The second query, though, is selected in the same way, in principle, is the most informative one, but conditioned on the fact that I've already asked one query and I know the answer to it. So I told my son it's less than 5, so the next query he asked me is probably, is it less than 3? Because he already knew that it was less than 5. So that's exactly the most informative second query, given that I know the answer. And then you keep going on, and you stop. You stop after a finite number of queries. When do you stop? You stop when you know that the information of all the remaining queries is 0. They're all going to be uninformative. Okay? So that's the algorithm. And so now you think, okay, this is great. It's now tractable. I'm just going to go ahead and implement it. And all I need to do is compute mutual information, and I'm going to be done. Okay. That's what anyone who read the cover book thinks when entropy is defined and mutual information. But when you actually have to compute, okay, what do I need? To compute all of these, I would need to have a joint model between Q of X and Y, right, to be able to compute that mutual information. And that requires, okay, if X is of dimension 2 or 3 and Y is of small dimensional, right, I can write down my generative model and I can probably get it. But if X is an image and Y is all of these interpretation of the scene in terms of describing the objects that are present and all of the relationships, we are talking about computing, first of all, learning a generative model on images, right? A question that has been around in computer vision since the 50s, and lots of great work was done with non-Markovian random fields and a million other things. We really, in the computer vision community, didn't make progress on how to build generative models that actually generate images that actually make sense up until relatively recently, like 2015 with GANs, generative adversarial networks. Then we had all of these variational autoencoders. Then there was the wave with flows, okay? And so that's where we are. Right now, we are beginning to have the technology to begin to learn these very complex generative models for images, and that was not available. So that's what we need to do next then. So I could spend a lot of time explaining how do we do it, but it would take me a long time, and you probably know a lot more than I do about these models in any case. But we chose to use these variational autoencoders, so I'll just have one slide on what they are. And so, again, what do we need to do? We need to compute the joint distribution of Q of X and Y in order to just find the first query. But then, eventually, I need to build many more generative models. I need to have the conditional distribution of Q of X and Y given the answers to the queries thus far. So I need to actually learn many generative models to be able to just implement this information pursuit. This is really challenging because, okay, suppose that I actually had a good training set of X and Ys. And so suppose that I could learn a generative model for Q of X and Y. But once you need to get to the conditional, right, it's like saying, oh, out of all the images of birds is now conditioned on the fact that the belly is yellow. So your training set is now dramatically reduced after one question to the subset of images that have yellow belly. Once you add a second question and a third question, your training set just keeps shrinking and shrinking and shrinking. So to train these generative models for conditional, you don't have enough data. Okay. So you need to make some generative model assumptions to be able to make this tractable. The simplest thing you could do is to say, I'm going to assume that all the queries are independent. But that doesn't make much sense in practice, right? Because obviously the whole point is that you're asking the second question depending on the answer to the first. So the second one is to say that if you know the class, then the queries are independent. And people have done some models, but it doesn't work as well. So what we did here was to simply have what is known as a latent variable model. So you postulate that there is some latent variable, z in this case, such that if you condition the queries on both the class and z, then the queries become independent. So for example, right, if you're trying to recognize birds, viewpoint, lighting conditions, they don't matter for determining the class of that bird. So that's exactly what I mean by latent variables that affect your observations, but if you knew them, then you could assume that the answers are going to be conditionally independent. And so that's what we do. So to build this generative model, the way it works is as follows. On the left, you have the answer to the queries and y, because in this case, we're trying to just build a joint generative model for Q of X and Y. You map that to what is known as a probabilistic encoder that predicts the probability of the latent variable given Q of X and Y. And typically, what is assumed is that that latent space is Gaussian. So therefore, it's characterized by some mean and some covariance. And therefore, this encoder ends up being a deep network whose input is the answer to the queries and the class, and the output is the mean and the covariance of the distribution. Once you have that mean and covariance, then you can sample and pass it through the decoder, which is going to be another deep network that produces the answers to the questions. And so this is exactly the probability of Q of X given Z and given Y in this case. And now you train this algorithm, and it is very classical to use the so-called elbow, and which is the criteria for training them. Okay, I'm going to stop there, but by and large, what's the message? The message is you need to build generative models on questions and answers, and that's generally hard, and there are many challenges, and so having good techniques for learning generative models is important. Having good sampling techniques, it's very important because to train these models, you're going to have to sample. So we tried many things, and we're using fairly simple techniques like Langevin. And you have to deal with the challenge that you have less and less training data the more you condition. So doing this in a clever manner is important. Okay, so with that in mind, let me now just walk you through a number of examples showing how this works in practice. So the first example is going to be relatively trivial. The goal here is simply to classify images of digits. And you can see this here. So this is the number 5. Very old task in computer vision from the 80s. At this point, it's kind of boring. Like if you publish a paper on classifying MNIST digits in computer vision, it'll be rejected because you can get 99.9999 accuracy on the data set with fairly simple and shallow deep networks at this point. So why in the world am I showing you an example with the MNIST digits? Rather than giving you the whole image and you having a deep network that predicts the digits, we are going to do it by only looking at 3x3 patches. Well, you could be looking at 1 pixel at a time, or 2x2 or 3x3. That's an arbitrary choice. So I'm going to choose my query set. The query set is going to be to unveil a 3x3 patch. And because the images are binary, if I was only unveiling pixels, this would be unveiling one query, which is this pixel white? Yes or no? That's what it is. So we are unveiling 9 queries at the same time. Actually, if I were to ask you, right, if I don't give you the image and I ask you which 3x3 patch should you look at first in order to determine what digit it is, which one would you look at first? Well, I guess you probably might not seen the data set, but I'm giving you examples. More likely than not, right, you think probably needs to be somewhere in the center because in the corners is generally going to be black. So if I unveil a black patch, it's not going to give me any information as to what the class is. Okay? So that's just to give you the intuition of what to expect. And we have tried this on 3 other data sets because they're all binary images of the same kind. So this allows you to do multitask because with the same query set, we can solve 4 different tasks. So I'm going to run the algorithm for you. So on the left, you're going to see the image, the true image that we're trying to classify. On the middle, you're going to see what the algorithm has seen, and has seen nothing at the very beginning, so this is all gray. And on the right is the prediction of the posterior, the class given the image. And it's all blue because the probability is 1 over 10 at the beginning. Like the algorithm doesn't know anything, it's just 1 over 10. So as I said, what patch should you look at first? Remember, the selection of the first patch is a function of the distribution. I've not seen the image. I know nothing about the image. So for no matter what image in the MNIST data set you give me, the same patch is always selected. And this patch in this case, roughly in the center, but not quite. And that patch is now white. And now you can see that the posterior begin changes. So the algorithm now thinks that it could be at 0. As 0 is consistent with that. It could be at 2, obviously that's correct. It could be a 4, that maybe not. Maybe a 4 that you like this, perhaps. A 6. So there are the 4 top hypotheses are consistent with that. Given that, the algorithm selects the second hypothesis. Now being a 2 is more likely. And like that, now you select the third query, and so on. See, the algorithm here is a little bit confused. You think it could be a 0. You could have maybe a slanted 0 like that. But it really thinks it's a 1, and you could have a 1 here, perhaps. Okay? So what is the intuition behind what the algorithm is doing? It's really trying to select the next patch that is going to be, to some extent, most discriminative among the 9 classes, given what I've seen thus far. So here is next. Now the algorithm is really convinced that it's a 0. But eventually, I think, after 8 queries, the probability of being a 2 is much higher. And then with 9, 10, 11, eventually the algorithm stops with 11 queries. And it got, with 99% accuracy, that this is a 2. Now you do this for the, I don't know, probably we did it only for the test set, so it's for the 10,000 images in the MNIST data set. And you can compute how many patches did I need to look at. And so this is the average, it's about 11. And then what was the accuracy? 99.15. So we lost a little bit of accuracy by doing this. So making an algorithm that is interpretable in the sense of explaining which patches you need to unveil, reduces the accuracy from 99.99999, which is what you can do with a deep network, to 99.15 in this case. These are now examples of other data sets like KMNIST. Here you see that you need more questions and that your accuracy went down. And fashion and MNIST, you need more questions, 40 patches in average, 60 patches in average, and your accuracy is going down. This is a conjecture, but we conjecture that this semantic entropy is potentially a measure of the task complexity. In a certain sense, the K-MNIST data set is harder to classify than the MNIST. We did experiment, actually, if you just add noise to the image, do you need more queries in order to classify? And the answer was also yes. And it's strictly an increasing function of the amount of noise you add. But formalizing that and building a theory of task complexity based on these notions is future work. Okay, so let me move to some of the other examples. So this is the example that I've given already. So this is a set of images. There are 300 attributes. We've trained a network that predicts each one of those attributes given the input image. And the data set, by the way, was already annotated with both the class of the bird as well as all of the attributes. Okay. And what this is showing simply is one run of the algorithm for this particular image. And the first question is always the shape, whether it's perching like. Then whether the shape is all-purpose. Green is that the answer was yes. Red is that the answer was no. And in this case, with 9 questions, you can see how the posterior is changing, right? At the beginning is, again, 1/10. But after already maybe 4 questions, only 3 out of the 10 categories are possible. And after already 5 questions, it's very zoomed in on the fact that this is a great crested flycatcher. So that's one example. This is the second example. Here is text classification. So this is what the data looks like. There is always a category, in this case, travel. There is a headline. And then there is a short description. So these are news. This is the Huffington Post. And these are examples of what the news look like. So there are 132,000 examples. And the task is to find the topic: entertainment, politics, travel, and whatnot. Here, we did a pretty bad choice in retrospect of the query set. The query set is whether a word is present or not. And we selected maybe, there are way more than 1,000 words in all of these documents, but we selected maybe the top 1,000. And then the algorithm is selecting one word at a time. What is different? Like in the previous applications, we just needed like 9 questions and we were done. 10 questions, 11 questions. So here, you can see a run of the algorithm. We needed actually 125 questions to predict that this text was about traveling. And the distribution began to be picked only about 50 questions or so. And the reason is that if you choose words as your query set, in this case, in most cases, if you ask the question, is this word present or not? In most cases, the answer is no. So that's an example of a choice of a bad query set because you, again, the principle of 50-50 is a good principle of selecting questions that are more useful. In fact, a question that is very rare, that is maybe very sophisticated, is never going to be a question you ask first. Typically, you ask more complex questions later. Next example is medical diagnosis. So this is a data set called SIMCAT 200. This is a data set of patients, and each patient has some disease. And each patient also comes with a list of symptoms as to whether they were present or not. And so in this case, maybe just to, I mean, we've done this in every example, but just to remind you, how do we go from data to what we're doing? We need to build a generative model for questions and whatever we're trying to predict. So here is the generative model for this binary vector of whether a symptom is present or not, and the disease. Okay. Once you have those generative models, we need to compute the most informative symptom, the second most informative, and so on and so forth. That's what the algorithm is doing behind. So here you can see itching of the skin, abnormal appearing skin. So again, green is the answer was yes, red the answer was no. And you keep going through whether a symptom was present or not. And after 15 queries, I think here is herpes. Right? Maybe I'm not going to go through this. It's a little bit more complex to parse, and for the audience in the back, it's going to be hard. But what we were trying to do here, by and large, what are these curves? On the x-axis is how many queries. On the y-axis is what is the accuracy. And we were simply trying to compare how our algorithm does relative to other algorithms. What other algorithms could you imagine? People have tried to do this with reinforcement learning, because you could think of, in reinforcement learning, you take an action, and given an action, you get a reward. So you could think of the idea of choosing the question as taking an action. And you could think of the reward as, did I classify right at the end? Right. And so you could also do things such as, if I take any of the best existing algorithms for producing heat maps, regions in the image, and I just classify based on those selected regions, how accurately do it? And so this is just to show perhaps here that you could also say, what if I choose the sequence of queries at random? So that's the green curve here, and you can see that it's in the middle. And obviously the blue curve, which is at the very top, is ours, which means that for all the applications in here, we are able to get the highest accuracy with the smallest number of questions, okay? Which is what the algorithm was designed to do, right? Because it's really, in theory, trying to minimize the number of questions that get to be asked in order to classify. So, in summary, I just wanted to say that we should really begin thinking about how to make AI interpretable. We should be thinking about how do we define explainability in the first place. Existing algorithms don't do that, and they do it a posteriori. We're advocating that it should be done by design. We proposed a way to do it, which is to tell the user to select these queries and have this algorithm that selects a sequence of queries and produces an explanation. And this framework is computationally intractable in general, so you need to do a lot of approximations to get it to compute. But we've demonstrated already in a number of applications and hope to be building more applications as we move forward. Thank you very much.
Okay. I think we're almost